Hello guys, and welcome to the third video of my math series. This time it is Intro to Fourier Series, where we will start with Fourier's theorem. So Fourier's theorem. Let f of t be a periodic function such that f of t equals f of t plus t for all t, with t being defined as the period of the function. Then our f of t can be decomposed into some constant plus n equals 1 to infinity an cosine omega n t bn sine omega n t, or from n equals minus infinity to infinity of c e to the I omega n t, with omega n is defined as 2 pi n over t. Okay, so what can this do for us? It means we can decompose periodic functions into sines and cosines. Base. Or the more advanced answer, we can rewrite from f of t basis to a quote-unquote wave basis. In fact, look up operator whose eigenfunctions are e to the I omega n t. Hint, it's a differential operator. So that's the next level. That's the next level of this convo. However, for now, we'll just focus on this stuff, okay? So, how do we get Cn? So if we want to decompose this, how do we actually get our constants? Well, if we have f of t equals the sum from minus infinity to infinity of Cn e to the, whether it's minus I or I, doesn't really matter. It's really based on convention. I'll do normal. Then we can multiply by e to the minus I omega mt and integrate. And integrate from 0 to t. So we have the integral from 0 to t of to minus I omega m t dt minus infinity to infinity Cn 0 to t e to the I n minus m 2 pi over t. This is not dependent on t. So it doesn't really matter in the integral. And what this does for us is this here. Since we're integrating from 0 to t, if n is not equal to m, then the integral equals 0. Wave along period. I.e., example, the integral from 0 to 2 pi of cosine t dt equals 0. So if n equals m, integral equals 0 to t of dt. Because we'll just have a 0 here, which equals t. Which means this whole integral reduces to what we like to call a delta distribution. And so it becomes integral omega mt dt, f of t equals, factor out the t, minus infinity to infinity, Cn delta nm 0, 0 unless, which means n and m become interchangeable, and we have Cn equals the integral from 0 to t, 1 over t, f of t e to minus I omega m omega n t dt. And that's our formula. It looks exactly like a Fourier transform. And that's because in some reasons, a Fourier series coefficient and a Fourier transform is the same. This is just how you represent the function in Fourier space. Now, for finally, to go from an and bn to c. So we can write an cosine whatever plus bn sine whatever equals, I'm going to break apart. So break apart into the same, so 1 to infinity. It's going to be c e to the I omega and t plus c star as I omega and t. Because this integral is from 0 is minus infinity to infinity, but we can break it into 1 by having c's and c stars. And so an cosine plus bn sine equals, it's actually 2. There's a factor of 2. There's a factor of 2 missing. But in fact, who cares about a factor of 2? Equals c cosine plus I c sine plus c star cosine minus I c star sign. And so we match coefficients, and we get we match cosine coefficients. So an equals c plus c star, bn equals I c minus c star. And there we go. There is your intro to Fourier series.